Okay, welcome to part two of our lecture series from Monday, April 3rd, where we're now going to describe what on earth a base is. So just like with acids, we have three different ways. That's an eraser. Oh my goodness. We have three different ways to define or identify a base. So let's start with our first, which is our Arrhenius definition. And again, I like to think about our Arrhenius definitions of both acids and bases as describing like how it is I could identify an acid or base just by looking at it. Like, what is it about the composition of an acid or base compound that tells me, oh, yes, this is an acid or this is a base? So, according to the Arrhenius definition, a base is a substance that contributes hydroxide anions to solution. So instead of contributing that acidic H+, we are now contributing base particles, which are hydroxide particles, hydroxide polyatomic ions. Now we have the same idea of dissociation being what determines the strength and weakness of a base as we do when we looked at the strength and weakness of an acid. It's just here, instead of looking at the dissociation between an acidic proton and some anion, we're now looking at the degree of dissociation or separation between the hydroxide anion and some cation. So let's talk about our strong bases. These are typically our group 1 and 2 metal hydroxides. So for example, like NaOH, potassium hydroxide, magnesium hydroxide, so on and so on. And if we're thinking about what makes these strong, we are going to show a complete or perfect dissociation from that hydroxide anion and its cation. So let's look at sodium hydroxide. So when sodium hydroxide is dissolved, we generate Na plus and OH minus ions in solution. And because this is a full dissociation, this is what makes us strong. And because that full dissociation resulted in us contributing hydroxide anions to solution, that makes us a base, according to the Arrhenius definition. Whereas weak bases, these are a little bit more interesting. So weak bases have partial dissociation and often react with water in solution to create hydroxide ions. All right. So there are a couple of examples we can look at here. The first, I think, let's maybe look at sodium bicarbonate. So we have NaHCO3 in the presence of water. So let's dissolve solid sodium bicarbonate into liquid water. All right, when I do that, I am going to create Na plus ion because sodium bicarbonate is an electrolyte, right? This is a fully soluble compound, so I dissociate into the bicarbonate and the sodium ions respectively. And then I've also got liquid water. And then what happens between the water and the sodium bicarbonate, specifically the bicarbonate, is what makes us a base. So I want to focus on just what's going on here. So I'm going to write a separate line where we've got the HCO3 or bicarbonate anion in the presence of water, which I'm going to write a little strangely. I'm going to write it as HOH, and there's a reason for this. Okay. So what happens in this reaction is because of the presence of this sodium bicarbonate, or namely this bicarbonate anion, water itself weakly dissociates and acts like an Arrhenius acid, meaning this H plus is donated. And because it's acting like a weak acid, this is going to have partial dissociation, which is what makes us weak. And this will form for us H2CO3 and the remaining hydroxide ion. So if you think about detaching this H and giving it to here, then we would result in just an OH minus left over, which is what makes us a Bronsted-Lowry base. Now, if you remember from our gas evolution reaction video, you might recall that carbonic acid, which is what H2CO3 is not something that is stable in solution. So it's even better to write this reaction that shows the decomposition or the gas evolution that results from carbonic acid being made in solution. So if I were to rewrite this, I would have my bicarbonate ion reacting with liquid water, which again I'm writing as HOH because I do want to show this. And if I remember what my carbonic acid decomposes into, that decomposes into CO2 gas plus liquid water. So these are the results of our gas evolution. And then, of course, we have our remaining basic hydroxide. So if I were to take all of these and give the net ionic equation, I would have bicarbonate ion reacting with liquid water. And because this is our weak base, it's the thing that is responsible for the contribution of hydroxide in solution, I have partial dissociation, and then that will create my dissociation products, I guess I'm just rewriting the same thing because ultimately my sodium will cancel. So I will have my CO2 gas plus H2O liquid plus hydroxide aqueous. Again, that was pretty redundant, but this is the net ionic equation. Now, weak bases, since they are kind of weird, right? There's no thing that contains hydroxide that will have any kind of poor dissociation unless we're looking at like slightly soluble things. But even then, it's not really a question of basicity then. It's more of a question of, do you create a solid or not? So anytime we're looking at weak bases, we're looking at interactions with whatever our anion is from some compound with water to generate hydroxide. And the whole concept of weak acid and weak base chemistry is really reserved for Chem 220. But I did just want to demonstrate to you, like some people will look and say, well, why is it that bicarbonate or sodium bicarbonate can be treated as a weak base? Same with ammonia. And the reason is for the following. It's the interaction between water and the bicarbonate ion that creates this basic hydroxide in solution. In fact, fun fact, you know how in the lab I have a bunch of sodium bicarbonate containers available at your lab bench to neutralize any acid spill? That's because I've got these basic particles that once I dump my powder sodium bicarbonate into my aqueous spilled acid, I create not only those basic particles to neutralize my acid, but I also see that characteristic fizzing that we associate with neutralizing some kind of acid spill in the lab. So this is our Arrhenius definition of a base. Simply anything that contributes hydroxide to solution. They could be strong or weak, where strong bases have full dissociation into some cation and the hydroxide anion, whereas weak bases generate hydroxide through some kind of indirect means via an interaction or reaction with water. So this is our first perspective of what a base is, like how you can identify a base. It's does it put hydroxide into solution? And up next, we're going to talk about how we can identify a base according to what it does, using both our Bronsted-Lowry and our Lewis definitions of a base.